Welcome to Chemistry 111 on this 11th of September. We will begin by finishing off Chapter 4. We will briefly, very briefly talk about the homework for Chapter 4. We will actually a little bit ahead of schedule because, and then we'll probably start a bit of Chapter 5. But looking at the syllabus, what the syllabus actually has planned is that we would continue Chapter 4 today and finish up Chapter 4 next week and start Chapter 5, finish that, and have another test right around the corner. I know it's like, oh, we just had a test. This test is going to be over only 2 chapters, so we're going to have a lot more stuff on electron configuration, a lot less math on this, though what math we will have will be on like properties of light, turning wavelength to frequency to wavelength. So what I've been noticing and what should be fixed before then is making sure you understand converting units. Speed of light is in meters. If the wavelength is in nanometers, you have to convert into from nanometers to meters. That's one thing I've been seeing, where if I have like 300 nanometers, that's going to be 3 times 10 to the -7th meters. It's going to be a really small number. And so when we get to the frequency, it's going to be a really big number, like something like to the +14th. So I saw a bunch of people goof up on a couple different conversions, and I just want you guys to recognize this, fix it, and if you need help, ask for help, and I'll be glad to take some time. But the last bit we have for this chapter is looking at the valence electrons and the condensed electron configuration. Last class, we learned how to give the full electron configuration, where we have the principal quantum number n, which related to the rho and the energy level and the orbit around the atom. So if I have a nucleus, we have the orbit number 1, orbit number 2, and so on, and it gets further and further away. As we go up in the periodic table, as we go from low numbers, hydrogen, to higher numbers, each row will tell the row number has to do with how many orbits it has available. Hydrogen only has orbit 1. Lithium has orbit 1 and orbit 2. Sodium would have orbit 1 and orbit 2 and orbit 3 available. And then we learned that as we move down the table and get more orbits, we get more subshells available. Row 1 only has S available. Row 2 has S and P. And we can see the S is related to the first 2 columns. The P is related to the last 6 columns. And as we move down to row 3, D becomes available, but it doesn't get used. 3D is not utilized until we get to the 4th row. And so as we work our way across the table, you go 4S, then 3D, and then back to 4P. And the same thing with lanthanides and actinides with the F. But it becomes very tedious to do the full electron configuration, especially because where the electrons actually react is at the outermost layer. You cannot get to the inner layers before going through the outer layers. You cannot penetrate the keep of a castle before you get through the outer walls. So the valence electrons is where the chemistry will take place. So we are going to condense this down so we only look at the outermost layers, or these valence electrons. And now we're going to do that by essentially abbreviating with our noble gas configuration from the row above it. The noble gas configuration. Noble gases by nature really, really don't like to react. They have a filled row, a filled orbital. When you achieve a filled orbital, you're in an energy low point. It's like I rolled a boulder, it went down a hill, and it ended up in a valley. It just stops. It can't get out of that valley. This energy valley is what's going to keep noble gases from reacting. So whenever we do an electron configuration, we find where is the element. Where is the element we're looking at located? We go one row up and all the way to the end to get to the noble gas. And we start from there. So lithium. Lithium is typically 1s2, 2s1. 1s2, 2s1. But lithium is second row. So I move one row up to row 1, all the way over to helium. 1s2, 2s1. Helium is the same as 1s2 because helium has that electron configuration. So we're saying helium 2s1. So what we're saying essentially is lithium only has one electron it will want to part with. And because of that, that one electron will keep it as a +1 oxidation state when it reacts. Aluminum. Aluminum is a little bit harder. Aluminum would be 1s2, 2s2, 2p6, 3s2, 3p1. Aluminum is what? Below boron. So we go for aluminum is one row up to row 2, all the way over to neon. Neon has the same as 1s2, 2s2, 2p6. So by using neon, we are cutting out all those core electrons. And then we can only give the ones we care about, 3s2, 3p1. We're cutting those guys out because aluminum, remember, aluminum likes to be +3. So where are the valence electrons? 2 in the s, 1 in the p, sum them all up, you have the number 3. And then going forward with zirconium. Zirconium comes into a transition metal. A little trickier. Zirconium is row number 5. So you go one row up, all the way over. All the way over gets us to krypton. Here's where knowing how to use the table is going to be your advantage. Krypton. Zirconium is row 5. So I go rubidium, strontium. Those are in row 5, the S blank, so that's 5s2. I run out of the S. I move into the D. But the D by nature is row -1. So this is row 5, so it's 4D. Row 5, so it's 4D. And zirconium is the second element in. So 5s2, 4d2. Otherwise, you have to do it all the way across. If you don't know how to read the table, you don't have the S and the D, you might have to do the whole thing and then simplify. But if you know how to read the table and you find where it's at, you can start from krypton and work our way down. Please note, we will only use the noble gases. We will not say strontium 4d2. Strontium will have krypton plus 5s2, but strontium is still reactive. there's 2 electrons here that will still react, that if we suck them up into the condensed electron configuration, we're going to hide some of the reactive electrons away. And we don't want to do that. We want to leave only the reactive electrons behind. Zirconium has a 2+ and a 4+ oxidation state. And we want to make sure everyone knows that. So we're not going to hide those away. Now, this right here, this practice is why we do this. Some of these are going to be easy. Some of these, the condensed electron configuration, are kind of stupid. But some of them, it's going to be a little bit easier to do the condensed. So beryllium, 4th element, element number 4, 1s2, 2s2. The condensed electron configuration. 1 row up, all the way over, puts me at helium. So helium, 2s2. Nitrogen, element number 7. 1s2, 2s2, 2p3. One row up, all the way over, still helium. Still helium. So it's helium, 2s2, 2p3. We don't want to abbreviate this as beryllium because nitrogen has 5 electrons. When we go to drawing Lewis structures for test number 3, we are going to use all 5 of those electrons to make bonds, to make lone pairs. We're not going to use those 2 core electrons. We are going to use 5 valence electrons to make bonds, which makes nitrates and nitrides and all that fun stuff. Sulfur, that's, don't remember the number, but it's right below oxygen. So sulfur, 1s2, 2s2, 2p6, 3s2, 3p4. Now, I may be doing magic here, not having to look at the table to do this, but I know where it's at practice. As you're doing this, you want to be looking at the table, working your way over. This is the 4th element in the nonmetal section, the P section. That's where I know where it's P4. Separating the 1s and the 2s from the 3s. 1 row up, all the way over is neon. This becomes neon. 3s2, 3p4. Starting to become more worthwhile to condense this. Zinc. Zinc's a little bit harder. It's the last element on the transition metals on the 4th row. So zinc, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Once again, practice makes perfect. I can do this because I've had years of practice. I've done this without needing the table in front of me because I've had years of practice and I don't change these examples very much. Separating the 4 from the 3. 1 row up, all the way over is argon. The noble gas before zinc is argon. So argon, 4s2, 3d10. Before you ask, well, shouldn't the 3d10 be incorporated into the 3p6? we're using all the electrons from that given row. Even though those 3d10 will not really react, we want to keep all the electrons from that row when we do this condensed electron configuration. Because sometimes those 3d will react. Then finally, lead, a serious pain in the ass. It is element on row 6. The second element into the p block on row 6. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. I'm just working my way across the table, mind you. Just S, D, P, S, D, P. Now I'm on row 6. 6s2. Now here's where it gets tricky. You notice if you look your way across the table, there's a little blank right below yttrium that says La-Lu. The lanthanides, that's where you get the lanthanides and actinides get shoehorned in there. So the F block suddenly rears its ugly head. F block is row -2. Row -2. So if this is row 6, this is 4F14. And then we get back to the D. The D are row -1. So since this is row 6, it's 5D10. And now we're back to the P, 6P2. That's a whole mess. But looking at lead, one row up, all the way over, we can abbreviate that whole top part is xenon. Xenon, 6s2, 4f14, 5d10, 6p2. It is a serious mess. And yeah, if you don't write all this down, that's fine. It's on the slide. I do it for this reason. It's on the slide. You can always come back to it. I think I'm on my own cord again. But the best way to do this is practice. There's a couple problems on the homework. What could I ask you on a test? I could ask you, do an electron configuration. I could ask you do a condensed electron configuration. I could ask you to identify the element based on the electron configuration. And in a few minutes, we could do the electron configuration of ions. So all these electron configurations have been on a neutral metal or neutral element of some kind. How do we deal with ions? We are going to add electrons or subtract electrons from these electron configurations. I'm going to jump ahead to the anions because those are the most easiest to understand. Yeah, most easiest. That's some good grammar there, Andrew. But so they're the easiest to understand in that we are going to continue with the building up principle where we put electrons into the lowest unoccupied orbital. So when we add electrons, we're going to just keep adding to where we're currently at, whatever row we're currently at. If we fill a row, we would move on to the next one. Just like we're moving to the left, moving to the right. So the example I give is fluorine. Neutral fluorine is 1s2, 2s2, 2p5. To add one electron, you would add it to the 2p5 so that you now have 2p6. Fluorine will be stable with 2p6. It will not want to add a second electron, because to add a second electron would put it into the 3s1. And to jump up a whole nother row is not electrically stable. It's like pushing a rock up a hill. We've reached the valley, the rock's stuck there. We don't want to add another electron. So we're going to add electrons. Nitrogen, I haven't given that example, but nitrogen would be 2s2, 2p3. So if you add one electron, you'd go to 2p4. If you add a second electron, you'd go to 2p5. You can add a third electron to go to 2p6. Nitrogen is the most stable in the 2p6 when you have a completely filled row. Now, cations are a little bit trickier. We're obviously going to be removing electrons, but here's the rule. We remove electrons from the highest energy, furthest out orbit first. We're going to remove them from the highest energy, furthest out orbit first. In all technicality, what that means is we're going to remove from the P, then the S, then the D, before we even touch the F. So if we have electrons in the p orbital, we attack the p first. Then if we have any electrons in the s, we remove from the s. And then we touch the d. Yes, technically 3d is higher energy than 4s, but 3d is closer to the nucleus. So when we're looking at that atom, 3d is going to be if 3d is here, 4s is here. If 3d is right here, 4s is here. So it's easier to take from the s before you can take from the d. So with that in mind, magnesium. Magnesium is 1s2, 2s2, 2p6, 3s2. Magnesium 2 plus, we take first one from the 3s, and then the second from the 3s. And you essentially have 3s0. 3s0. So it is 1s2, 2s2, 2p6. In those two examples right there, you'll notice magnesium 2 plus and fluorine 1 minus both have 10 electrons. This is a situation known as an isoelectronic system. They are systems where they have the same number of electrons. And we can say based on the next chapter, we can say some comparative features of these two. And we'll talk about them. But I want to briefly give an example of this electron configuration in terms of a transition metal. Let's erase this and do iron real quick. Just iron. Iron's a perfect example. Iron has a +2 and a +3 oxidation state. So iron would be argon 4s2 3d6. This is iron. So iron 2 plus, we first attack the P. There's no P. The next attack the S. There is an S. So iron 2 plus would be argon 3d6, because we've removed our 2 electrons from the S. If we went to iron 3 plus, well, there's no more S, so the last thing we can take from is the D. 3d5. Now, because of this 4s2, most transition metals will have a 2 plus oxidation state in addition to whatever else they have. Most of those will have a 2 plus oxidation state in addition to a second charge possibility. But that is why it comes down to this removing of the 2s electrons. Now, iron, there's a funny little fact that removing a half-filled d orbital is particularly stable. So 3d5 is really stable, and we don't want to touch it after that. So iron will not lose any more electrons, really. Okay. This last slide, we'll not really worry about this for the test, but to sum this up, and as a too long didn't read, is there is a mathematical quantities and rules that can describe the position of every electron within a system. And in terms of principal energy level, the shape, which is the angular momentum, the degeneracy, which orbital of that shape do you have, which is the magnetic, and the spin, which is up or down. And the Pauli exclusion principle essentially states that no two electrons can have the exact same designation. If I'm given the example of just hydrogen, well, no, let's go helium. Helium, there's 2 electrons. 1s. 1 electron up, I'm going to call that electron A and electron B. Electron A would have N is 1, let's see, L is 0, M sub L is 0, and M sub S is plus a half. That's the A. The B would be 1, 0, 0, negative a half. I could not have those both be the same in every aspect. If I have this, those have to be different. If I have a p orbital, 1 electron, if they're both spin up, they have to be in a different orbital. This has to be A, this has to be B. If they're both in the first blank, they have to be opposite spin. Essentially, the Pauli exclusion principle put into mathematical quantities. It's not super important. Sometimes homework questions get thrown in about this. I've already checked. It's not a big deal. There's not really about this. So we're not going to worry about this. This is too much math of a not that much math chapter. But that is that. So that's the end of chapter 4. I'm going to quickly throw up some homework just so I can show everybody the assignment. It is not hard. We do not have homework due this week because we just had the test, but use this as a good chance to get ahead. There is only 10 problems on the proper assessment, but we still have like one little reading assignment and the learning curve for chapter 4 due next week. And then the week after that, we have chapter 4. Yeah, there we go. So use a chance to finish chapter 4 homework, since we finished this well in advance. There is a couple questions about, oh, for God's sake. There's a couple questions about quantum numbers. There's a couple questions about the speed of light. I just want to show you a quick setup. Clear. For God's sake. What's going on? Okay, there it is. Okay. There's some about looking at this. Remember, this one asking you frequency, wavelength, and amplitude and energy. Remember, frequency and energy are directly proportional. Frequency and wavelength are indirectly proportional. So a long frequency means a large frequency means a small wavelength. Amplitude, we didn't really talk about, but amplitude is the height of the waves. The height of the waves. I'm going to skip that one. This is the one I really wanted to show. And even though I can work this out for you, you will have a slightly different number. So this one is a little tricky in that it's not quite the speed of light. It's actually dealing with sound waves. But the same concept will still hold true. It gives you that. What is the wavelength of a middle F? When I did this yesterday, it was like, I don't know, E. They give me a frequency and 349.23 hertz. And they say, what is the wavelength in centimeters? And they give us the speed of sound is 343.06 meters per second. That won't change. That's the speed of sound. So the big difference here is instead of the speed of light, we're dealing with sound. But the same equation still holds true. C equals frequency times wavelength. So if I divide both sides by frequency, I should get wavelength. Now here's another tricky part. It gives you in hertz, but 1 hertz is equal to 1 inverse second. 1 inverse second. Let's go. Oh, can't see up there. 1 hertz is equal to 1 inverse second. So we have essentially 349.23 inverse seconds. So all we have to do, 343.06 meters over seconds. I'm going to divide by 349.23 inverse seconds, which makes this 1 over seconds is the same as seconds over 1. What does that do? That cancels out my seconds. What are the units we're going to end with? Meters. One last thing. What are the units they ask for in the answer? Centimeters. So we do a conversion here. There in 1 meter, there is 100 centimeters. Meters, meters. Make sure you understand how to type this into your calculator. I've seen some lab work where they set the problem up perfectly right, and magic happens somewhere between the setup and the calculator, and I get a number I have no clue how they got. I have no clue how they got. So please check this. Typing this in, 343.06. I multiply this by 100, and I divide that answer by 349.23. I get 98.23 centimeters. Before you type that in on your answer, keep in mind, your answer may be slightly different. Your answer may ask for a different note. The setup will be exactly the same, but this number may be slightly different, so you can't just use 98. But if you can set this up, you can solve it easy. Energy one, that one's pretty straightforward. This one is the only other one I really want to talk about, and impossibilities. Which of these are impossible and which of these are possible? So I can't really make out too well because of fogging, but right there we have various orbitals. The thing to remember, we typically go up to level 7 because we only have 7 rows of known elements. S shows up on row 1. P shows up on row 2. D shows up on row 3. So there is no 1P. There is no 1D or 2D. So the possibilities are 3D, 0P, 3P, 1D, 2F. 3D, perfectly possible. 0p, there is no principal energy level 0. That is an impossibility. 3p, well, there's a 1. If there's a 2p, there's also a 3p. 1d, that's an impossibility. D does not show up till row 3. 2f, 2f is an impossibility. F doesn't show up to 4. So that's what it means, what is possible and what is impossible. I saw things similar to that. These may not be the exact same for you, but the same general premise. They're going to throw one that's a D that can't exist, an F that cannot exist because they come too early. They might give you a principal energy level that's impossible. And then there's some like, oh, that's a good question. There's I think there's some putting electrons in. I think there's one of them that asks you to how many electrons are in the D row of this element, and then they ask you how many electrons are unpaired, which is a good one. You would have to put the energy level diagram, put the electrons in, pair as many up as you have, and then see how many are actually paired and unpaired. That would be a perfectly reasonable question to ask on the test. But there's only 10 questions on this homework assignment. So utilize this as a chance to get that done. I'm not asking much. I'm just asking. Okay. Let's look at chapter 5. We're not going to get too far in here, but I want to try to keep relatively close to the Tuesday, Thursday class. So when we finish this, we will start reviewing for test number 2. I'm not sure exactly when it will be, but probably 2 weeks from, or like maybe 1 to 2 weeks from this Sunday, something like that. Not sure exactly when, but we'll probably have started chapter 6 around the time we're doing this. Okay. I gotta throw that up. Okay, here we go. So chapter 5, periodicity and ionic bonding. So it's not a hard chapter, but we're going to learn about trends. We're going to learn about trends, and we're going to relate them to that quantum stuff we just learned. So the basic idea here is that if we understand this quantum stuff, this valence electron theory, we can understand why the periodic table is laid out how it is. That even though the principal energy level is different, the number of valence electrons in a column is always the same. And because the number of valence electrons are the same, they'll typically react similarly. Alkali metals, whether it's 2s1, 3s1, 4s1, 5s1, they all have one valence electron. Thus, they will typically lose it to become +1. I mean, we have each halogen will have will have a total of 7 valence electrons, whether it's 2s2, 2p5, 3s2, 3p5, 4s2, 4p5, will all be 1 electron shy of a filled orbital. And so they'll typically want to gain 1 electron when they form ionic compounds. We learned this when we were trying to put these guys together. We move this element 1 element over to get to a noble gas. Well, that's had to do with the valence electrons. We could set this up so even if we didn't understand this, we could kind of predict the charges. But now that we have this, we can predict the charges a lot more accurately. But this noble gas configuration is really, really, really stable. So, Okay. And one of the first trends we'll talk about is atomic size, which will help determine a lot of the other trends, because we're going to have a lot of electronic interaction between the electrons and nucleus. So the atomic size will have to do with how the nucleus interacts with the electron cloud. The nucleus is a big chunk of positive in the center, constantly pulling that electron cloud in. That electron cloud is constantly trying to escape because the electrons will be pushing each other outwards. As they get closer and closer to the nucleus, the electrons will start repelling each other back outwards. And so there's a constant fighting force. But remember from the Rutherford's gold foil experiment that most of the atom is empty space except for that electron cloud. So that atom is mostly that electron cloud. So the electron cloud is going to be the thing we're really going to be considering when it comes to this. Remember that opposite charges attract, like charges repel. If I up the strength, like up the charge, attraction should go up. For example, if I use a fridge magnet, it's going to be really weak. If I use a rare earth magnet, those things can pull a paperclip through your hand. You increase the strength of a magnet, you could crush, pinch fingers. And also, you decrease the distance, you increase the strength of whatever attractive or repulsive forces. You bring two magnets closer and closer together, they're either going to snap together or they're going to shoot apart. So, the first thing we're going to talk about is the effective nuclear charge. This is a little trippy. It's a little trippy, but the reason why the effective nuclear charge is so important is because when we look at an atom, what's one thing we mentioned when we talked about the atomic mass and the atomic number? We called the proton, neutron, and electron count. For most neutral atoms, the proton and electron count are identical. So how can we have a difference between them? Lithium has 3 protons, 3 electrons. Bromine has 35 protons, 35 electrons. Why are they different? Why are these guys so different? They have a completely different, they still have a 1-to-1 ratio. And that's because, well, the nucleus and the electron cloud are set up completely different ways. The nucleus is the big chunk of positive. All 3 or all 35 protons are stuck in a big, dense core of positive. Those electrons are going to be completely spread out. Especially, they're going to be spread out into many different orbitals, many different layers of charge. And these layers of charge will actually shield other layers. Each outer layer is going to be shielded by the layers before them. In the case of lithium, 3 electrons has 2 electrons in the core that's going to shield the outer electron. Let's see. Bromine is going to have what? 3 layers in the core that's going to shield the outer electrons. There's going to be a lot of electrons in the outer level that I'm not even going to try to get them all. But these layers are going to essentially shield the outer layers from the core. Just the same way we put nuclear shielding around a core so the scientists and the physicists and the engineers working the nuclear power plant don't die like immediately after they start the plant. The same way we put lead shielding over the body parts that we don't want to be X-rayed. Same way that we're essentially trying to shield the outer layers. And so the core electrons are shielded from the nuclear charge Z. So we can get a Z effective. The effective nuclear charge felt by an electron is going to be some ratio of Z minus S. S is the shielding factor. Now, there's ways to calculate this, and I'm going to give you them, but I'm not going to actually ask you about them. It's basically that an electron in the core shields by a factor of 0.85. Electron in the valence level shields by a factor of 0.35. I'm not going to ask you to do any math with those. But basically what it means is core electrons are almost a one-to-one shield. Almost. The valence electrons don't shield each other very much at all. And so what we get is we get this pattern. So looking at this graph right here, this little chart, the purple right there is the actual nuclear charge. As we go across the table, you see the number of protons go up linearly. 1, 2, 3, 4, 5, 6, all the way up. The black bar, or the kind of like, I don't know, blackish, dark bluish bar, is the effective nuclear charge. So what happens? See, it goes up, drops. Goes up, drops. Up, and you could predict it's going to drop again. Where's that drop occurring? It's occurring right after the noble gas. What's happening between the noble gas and the next element? We're adding a whole nother row. We're adding a whole number orbit. So we're going hydrogen, helium. I filled the 1s orbital. They're valence electrons. They're shielding each other. And then we add to lithium. So now we've started in on the 2s. We see a big drop because suddenly that 2s is shielded by the core. And it's going up and up and up because we're adding more electrons. The core doesn't get any bigger when we add more electrons going across. The valence electrons get bigger. We hit the peak at neon. And then what happens? We add to the 3s. Suddenly the core is now the 1s, the 2s, and the 2p. So the core got bigger, so the shielding got stronger. And so we're putting further and further and further away. So what we see is, in general, shielding only goes up slightly as we move down the table, but shielding, the Z effective goes up only slightly as we move down the table, but Z effective increases greatly across the table. You notice hydrogen is slightly below lithium. Lithium is below sodium. You can say sodium is going to be slightly below potassium. And we could see that trend. And where I'm going to leave us today to catch us completely up is with this slide, atomic radius. That we are going to describe the atomic radius in terms of this electron cloud. How we can imagine this is the Z effective is going to affect that electron cloud. Each orbit gets further from the atom. Each orbit gets further from the atom. So as we move down the table, orbits get bigger. 1s right there, 2s, getting further and further away. We're getting further and further away, so the atoms get bigger further down the table. But as we move across the table, what do we see about the Z effective? The effective nuclear charge goes up. So if we're not adding more orbits and we're adding more attraction, they're pulling these guys in. We're pulling these electrons closer into the nucleus and holding them tighter. So the elements in the top right end up being the smallest. The elements in the bottom left end up being the biggest. If you think of these electrons as prisoners in a giant prison complex, as we move from, you need very few guards to watch all the prisoners. As we move from left to right, we may be adding more prisoners, but we're also adding more guards. So we're adding like, oh, I add one more prisoner, one more guard. Suddenly, the guards have a better control of everything as we move from left to right. As we move from top to bottom, we're adding whole new orbits. We're adding a new wing onto the prison filled with hundreds of guards. But we're adding like 2 guards to guard a whole wing. So they're getting bigger and bigger. They're less well guarded. So we're getting further and further away from the nucleus. So the atomic radius has a general trend that the largest size is the bottom left, the smallest size, the top right. And we're going to use this size when it comes to talking about ionization energy and electron affinity, which we'll talk about on Monday. That's all I got for today. We've caught up. Thank you for your patience.